Good afternoon. So in today's lecture, we will deal again with series that may have negative terms, and we will learn some powerful ways to decide whether they converge or not. We will introduce yet some other definitions and concepts. And I should point out that if you feel overwhelmed, remember to be patient because the whole topic is actually much easier than it may seem. The difficulty lies in the lack of practice and familiarity with the terms. So you need to give it time and you need to really practice as much as possible with all of these theorems and definitions we learn. But as I hope you noticed already, the amount of work or the math involved is not that heavy. Also, later on, we're going to have a list of, or you can make yourself actually a list of all these properties we learned so far, like all the convergence theorems we learned, and have that handout in front of you, and basically for every problem, compare it with the handout and see which of the properties or theorems we learn is applicable to the problem itself, and then in time you will maybe not need the handout anymore. So notice the title of the lesson is called Absolute Convergence and the Ratio and the Root Test. So let's talk about what we mean by absolute convergence. So as a remark, this concept deals with basically looking at the series obtained by ignoring the negative signs if they exist in the series. So this is not really a formal definition, but I just wanted to put this remark here just to understand the main idea. So you have a series that it may contain both positive and negative terms. Based on that series, you can obtain a new one by replacing essentially the minus with plus. And then you will obtain a new series with positive terms. And then we'll see what we can do with that and what that can tell us about the original series. So formally, basically, the idea is this. So given summation from 1 to infinity of an with an real numbers, either positive or negative, right? I mean, an can be any real number. We look at the series made of the absolute values of an. So the absolute value, remember, if there is a negative sign, if an is negative, the absolute makes it positive. If it is positive to begin with, absolute value of an will leave it intact. So as an example, let's say I start with the series given by minus 1 to the n minus 1, 1 over n, which again has the terms 1 minus 1 half plus 1/3 minus 1/4 and so on. We will look at the summation from 1 to infinity of the absolute value of minus 1 to the n times 1 over n, which basically this is just summation of 1 over n, right? Because absolute value of, so if we expand this, that's going to be absolute value of 1 plus absolute value of minus 1 half plus absolute value of 1/3, absolute value of minus 1 over 4, so on and so forth. This essentially becomes summation of 1 over n. So when you look at the series with absolute value of an, is essentially looking at the series obtained from the original one, but by ignoring the minus signs, or by replacing minus with plus, basically. We do this because often the resulting series with positive terms, this one here with the positive terms, can tell us a lot about the original series. And this is basically related to the new concept that we're going to introduce today, the concept of absolute convergence. So if it happens that the series with positive terms converges, as it turns out, there is a theorem which states that the original one converges as well. So let's write a definition. First of all, we say that the summation from 1 to infinity of an is absolutely convergent and we denote this by AC, if the related series with positive terms, summation of from 1 to infinity of an, is convergent as a series in its own right. So this, again, tends to be a little bit confusing because people sometimes don't focus primarily on the fact that these are two different series, right? So when we talk about one series being absolutely convergent, we use this concept, we define this concept via a different series, the one obtained by looking at the series with positive terms. So now, of course, the reverse is not true. The converse is not true. If a series is not absolutely convergent, the original one may be either convergent or divergent. We just have to basically use different means to establish that. So, by the way, what I just said here, and let's write it formally as well, this is called the absolutely convergence test, which simply states that if summation of absolute value of an convergent, then the original summation from 1 to infinity of an convergent as well. So take a moment, pause if you need to write this down, and then we're going to just analyze this via examples, because that's the easiest way to make sure we don't confuse the terms. All right. So as an example, so suppose we have summation from 1 to infinity minus 1 to the n minus 1, like I said before, 1 over n squared. We made this in a previous lecture. This by itself is a series with negative term, positive and negative terms. So this is an alternating series. So the absolute convergence test simply says that instead of looking at the original one, we're going to look at the series obtained from the original one by taking the absolute value of the terms in the summation. So I'm looking at the summation from 1 to infinity of absolute value of minus 1 to the n minus 1, 1 over n squared, which is 1 over n squared. Now, this becomes a series with positive terms, which is eligible for all tests involving series with positive terms, including in this case, for instance, the p-series test. This happens to be a p-series. So this is p-series with p equals 2 greater than 1. Hence, it is convergent. Again, just pause for a moment. What I just said is the series obtained from the original one by taking just replacing the negatives with positives, we concluded that this new series is convergent. And the absolute convergence test simply states that if that's the case, then we can conclude that the original one is convergent as well. In fact, by the definition above, it is absolutely convergent. Now remember, we learned something called alternative series test. This is another option here. We'll leave that for a moment. All this absolutely convergence test states is that we can derive the convergence of the original series by looking at the series with positive terms obtained from this original one. It's a unidirectional thing here. I mean, you cannot conclude in reverse, right? If it's not absolutely convergent, the original one may or may not be convergent. So we're going to illustrate this with p-series because these are the easiest ones to handle on the next page. So let's stay tuned. All right. So for example, Let's look at summation from 1 to infinity, minus 1 to the n minus 1, 1 over square root of n. And let's say the first question, is it absolutely convergent? Well, to answer that question, I'll have to look at the summation from 1 to infinity of absolute value of minus 1 to the n minus 1, 1 over square root of n. That ends up being summation from 1 to infinity, 1 over square root of n. This is again a p-series because you can write it as 1 over n to the 1/2. So it's going to be a p-series with p equals 1/2, which is less than 1. What do we know about p-series with p less than 1? Those p-series are divergent. So the answer to the question, is it absolutely convergent, is no. Not absolutely convergent. Now, this is the key thing, and remember, it still begs the question, is the original one convergent or divergent? We don't conclude divergence from the absolute convergence test. It's a unidirectional theorem. I'll illustrate immediately with some arrows, but absolute convergence implies convergence. Not absolute convergence implies nothing. It may or may not be convergent. You have to use a different test. So all we establish is that it's not absolutely convergent. Now, in our class, the only tool in the toolbox left for an alternating series like this is to simply use the alternating series test and establish whether it's convergent or not. What does the alternating series test says? Well, I'm looking at the sequence that's separated from the minus 1 to the n minus 1, 1 over root n, and I'm going to check to see if it's decreasing. There are two conditions, remember, on the alternating series test. That means 1 over root n plus 1 less than or equal to 1 over root n. Yes, is decreasing. Bn goes to 0. Is the limit of 1 over root n equal to 0 as n goes to infinity? Yes. So then the summation from 1 to infinity, minus 1 to the n minus 1, 1 over root n, is convergent, but not absolutely convergent. So as the name implies, absolute convergence should feel like a stronger statement, essentially. Absolute convergence is more than just convergence. Absolute convergence means, again, that ignoring the minus signs, you still have convergence, and that automatically implies convergence of the original one. When the absolute convergence test works, you don't need to look at the original one. That's the advantage, because we have more tests that deal with positive terms. That's why it's advantageous to check first if it's absolute convergent. So schematically, basically, we can write these results like this. Is it absolute convergent? If yes, then it implies convergence. But that's the key thing. I don't even have to look at whether it's convergent or not, the original one. I establish absolute convergence, I'm done. The original one converges as well. Is it not absolute not absolute convergent, then nothing can be said. The original one, right? So let's say this is the original one. To make this schematic here, the original one can converge or diverge. Both possibilities can happen. You just have to use another test. In particular, we're going to use the alternating series test. But you see, this is why series which have negative terms but are not alternating series, that's why they are more complicated to deal with if they fail to be absolutely convergent. Because we don't really have that many tests for, we just have the alternating series test, but that works well only for alternating series. But that's not going to be the object of our class, basically. So let's see. So once we establish this distinction between absolute convergence and oh, there is another definition, and then we can move on to the more powerful ratio and root test. So let's write it here as a definition. If a series is convergent but not absolutely convergent, then it is called, or it is named, conditionally convergent. Or CC. It's just a matter of terminology, basically. So let's finish this page with another quick example. So summation from 1 to infinity, minus 1 to the n, 1 over n third. Is it AC? Well, I'm going to look at the summation from 1 to infinity, minus 1 to the n, 1 over n third in absolute values. That's a P series with P greater than 1, which means convergent. So for the original one, yes, it is absolutely convergent, and therefore convergent as well. You don't even need to say this, basically, I mean, because absolute convergence implies convergence. All right, so on the flip side, summation from 1 to infinity, minus 1 to the n, let's say 1 over n, is it absolute convergent? Well, I'm going to look at the summation of the absolute values. Let's say minus 1 here too. I'm going to write minus 1 here because that's how we set up these series, starting with positive term. Doesn't have to be, but just to keep the pattern. This is a P series with P greater than P equals 1, which is less than or equal to 1, obviously, so it's divergent. So it's not absolutely convergent. However, it is conditionally convergent by the alternating series test, right? If I look at, so not absolutely convergent, but conditionally convergent by the absolute, by the, like I said, by the alternating series test, right? 1 over n decreasing, 1 over n going to 0. So let's move on with the ratio and the root test, and then more examples down the road. All right, so the ratio test establishes a theorem for absolute convergence, and basically it's based on a limit that you need to compute. So let's say we have a series, again, with positive or negative terms. And then we have basically in the ratio test 3 cases. So in all cases, basically you compute the limit as n goes to infinity of the absolute value of the ratio between an plus 1 and an. And let's denote this limit by L. So this is essentially the computational part of the test. You take an plus 1, the n plus 1 term, divided by an in the absolute value, which will, remember, kill all the negative signs, and compute this limit. Now, because this is the limit of a positive term sequence, because you have those absolute values, you essentially have a finite number, or maybe divergent, maybe infinity. In any case, the convergence can be established, or the divergence, only under 2 possible cases. In all other cases, the limit basically, I mean, in all other cases, the test fails, so you have to use a different test. So you have basically 3 cases. If this limit L is less than 1, then the original series, summation from 1 to infinity of an, pay attention here, is absolutely convergent. So obviously it gives you the convergence as well, right? I mean, absolute convergence implies convergence. And in fact, you can even write here, therefore, convergent. The second case, if this limit is strictly greater than 1 or infinity, then the series summation from 1 to infinity of an is divergent. So it gives you these two extremes, divergence of absolute or absolute convergence. It doesn't give you conditional convergence that we talked about before. So in the third case, if the limit is equal to 1, the test is inconclusive. Must use other tests as appropriate. The root test is very similar, except you do a limit of a different type of sequence, but we'll get to that when the time comes. So we're not going to prove this, we'll just apply it with examples. And let's start with one example involving, so let's look at the following example. So suppose I have summation from 1 to infinity, n 3 to the n over minus 2 to the n minus 1. This is actually an alternating series. You can pull the minus 1 to the n minus 1 out, though we don't need to do that for now. If you want, you could do this just to see it as an alternating series. So this is minus 1 to the n minus 1, because 1 over that it's the same, and 3 to the n, 2 to the n minus 1. And so let's apply the ratio test. Now, one key thing to do, and you need to practice with this one, when you make the substitution, make sure you do it carefully. So an in the problem is n 3 to the n over minus 2 to the n minus 1. You're going to need an plus 1 as well. That means everywhere in the sequence you need to replace n with n plus 1. So go slow and make sure you simplify carefully, because if you make a computation mistake, it's not going to work. So n is replaced by n plus 1 everywhere. And then you form the ratio under the absolute values. So an plus 1 on the top, n plus 1, 3 to the n plus 1 over minus 2 to the n, because 1 minus 1 cancels. And divided by an means times the reciprocal of an. So, well, let's write it down actually like this, like big ratio. But later on, just do the simplified ratio from the beginning, just to not waste too much time. So when you divide one fraction to another, when you divide to the fraction, it's like multiplying by the reciprocal of that fraction. So it's multiplied by the reciprocal of an, minus 2 to the n minus 1. Over n 3 to the n. Then you need to simplify everything that can be simplified carefully. And in order to compute the limit, it helps to actually pair these similar terms together. That's another trick of the trade, so to speak. So for instance, write together in a fraction n plus 1 over n. These can be simplified, but put them together. Now, minus 2 to the n minus 1 goes away, and you're left with minus 2. Right, so you have basically 1 over minus 2. And 3 to the n simplifies with 3 to the n plus 1, and you're left with 3 on the top. So 3 over 1. Now, remember, n is a positive number, so now it's time to take into account the absolute value, which will essentially make this a positive quantity. So it's going to be 3 over 2 n plus 1 over n. Now, or if you want it as a single fraction, that's 3n plus 3 over 2n. Remember, the limit is given by the ratio of the dominating terms. The limit of the ratio of the dominating terms, which is 3 over 2. So my limit is 3 over 2 greater than 1, hence the original series this given series, in other words, is divergent. So we'll move on with other examples, but in a nutshell, this is how the test works. You compute a limit carefully and compare that limit with 1. Now make sure you don't confuse it with the limit comparison test, in which the limit just needs to be a positive number. The limit comparison test compares the given series with positive terms with another one. This one is just uses the same series, and you compare one ratio, basically the ratio between two nearby points in the series, an plus 1 over an. So let's stay tuned for more examples. All right, so here's another example. And notice this one has positive terms. The ratio test still applies, except that the absolute value won't have any effect. Right, so the absolute value of 5 to the n over 2n factorial is going to be still 5 to the n over 2n factorial. So you don't need to bother writing the absolute value anymore in this case because all terms are positive. So in general, notice that ratio test is really, I'm going to actually write this remark after we do this example. So what I was going to say is that ratio test works very well if the terms involved in the series are exponentials, like 5 to the n, or in the previous example we had 3 to the n plus 1 or something like that, and factorials. So combinations of exponentials and factorials works very well with the ratio test because you have nice cancellations and the limit that you need to compute tends to be easy to compute. And there are some notorious cases in which the test fails, but we'll get to that in a minute. So remember, for the ratio test, we need to compute the limit of an plus 1 over an. And again, in this case, we're not going to bother with the absolute values. So an plus 1 is 5 to the n plus 1 over, pay attention here, that's 2 quantity n plus 1 under the factorial. And then times, over the original an, which is the equivalent to times 2n factorial over 5 to the n. So make sure you simplify factorials carefully. Again, remember the trick to just combine the terms that are similar into the same fraction. 2 quantity n plus 1 is 2n plus 2 factorial. Now, when we simplify the factorials, let's start actually with 5 to the n. So first of all, 5 to the n cancels. And you're left with 5 on the top. 5 over 1 if you want. And when we cancel the factorials, remember the smaller factorial disappears completely because it's swallowed by the bigger factorial. So all you do is you write the remaining terms after 2n. And there's 2 of them, right? So after 2n, you have 2n plus 1, and then 2n plus 2, which is the last factor in the 2n plus 2 factorial. So if you look here, the limit is rather straightforward. Is 5 over 2n plus 1 over times 2n plus 2 is really 5 over infinity, right? It's 5 over something that goes to infinity, which obviously is 0. And 0 is less than 1, hence summation of 5 to the n over 2n factorial is absolutely convergent, hence convergent. Again, notice that if the series has positive terms to begin with, the distinction between absolute convergence and convergence is non-existent, right? There is no, basically, because there's no difference between the one with the absolute values, right? All of these are positive terms, but the test works just as well. It's just that there's no distinction between AC and C. Absolutely convergent and convergent. So let's write that remark that I promised. The ratio test works for series containing, it's not guaranteed to work, but in general, if you just see that the series contains containing exponentials, factorials, so exponentials and factorials. These type of series work well with the ratio test. There are some caveats which it's very important to be aware of them so that you don't waste time. So again, pay attention here because what I'm giving you are some time-saving devices here. So let's write another remark. The ratio test always fails. And I'll show you with an example. So always fails if an, the sequence in the summation, is made of only, the keyword is only, polynomials in n, or radicals and logarithms of polynomials. Because that lands you in the third case, which we didn't discuss yet, when the limit is 1 and in which the test is inconclusive. So let's do, so first of all, yeah, let's do a full example. So suppose you have, for instance, summation from 1 to infinity of 2n plus 1 over 3n squared plus n. And let's say you try ratio test. Well, an plus 1, again, these are series with positive terms. I don't have to bother with the absolute value. So an plus 1 is going to be 2 quantity n plus 1 over 3 n plus 1 squared plus n plus 1 times 1 over an, which is going to be 3n squared plus n over 2n plus 1. So when I take the limit of this is again infinity over infinity. And all I have to do is to look at the dominating terms. So to speed up the process here, I'm going to just expand just a little bit. So this is 2n plus 3 on the top, 3n squared plus n. And on the bottom here, if I expand this stuff, I'm going to end up with 3n squared plus 6n plus 3 plus n plus 1 times 2n plus 1. Anyway, so that we don't waste too much time, remember this limit is going to be decided by the ratio of the dominating terms. The dominating term on the top comes from 2n times 3n squared, which is 6n third. And the dominating term on the bottom is again 6n third. The rest of them have lower power, so that won't matter in the limit. But notice the key thing is that the limit is going to be 1. So the test fails. We can conclude from the ratio test whether this is convergent or divergent. So that's a very important thing to remember, because otherwise you will waste a lot of time. And in retrospect, you could see why that's the case. If I look, just stare a little bit for a moment on the original series here. Notice the dominating terms, right? They are 2n and 3n squared. If in the dominating terms I replace n with n plus 1, the dominating terms are still the same. So it's not a surprise that when you put them all over each other, I mean an plus 1 over an, it's not a surprise that you're going to end up with 1. So always fails when you have these combination of polynomials. And the same is going to be true for logarithms of polynomials. Again, if I replace, if I have, let's say, ln of n, and I compare it with ln of n plus 1, when I put them together into a limit, a ratio like this is going to approach 1. You could do a quick L'Hopital rule, and the ratio test fails. So then what do you do in this case? Well, first of all, remember this trick so that you don't even try it, so that you don't waste time. And usually, if you have positive terms, limit comparison test will work. I'll show you on the next page immediately to finish this discussion on this example. Or alternating series test if you have an alternating series. So let's move on with the next page. All right, so I wrote again this series, and again the ratio test fails. Instead, let's use the limit comparison test. In the limit comparison test, remember the idea is to pick another series to compare it with. One that will give you a finite limit when you take the limit of an over bn. That's the idea in the limit comparison test. And I remember that only works for positive terms. And the key thing, I mean, the little hint or trick is to pick bn to be the series made of the dominating terms. So for example, n over n squared in this case, which is 1 over n. That's the one that gives you the correct limit. Remember, in the limit comparison test, that limit just needs to be strictly positive. That's the only goal in that case. And if the limit of an over bm is strictly positive, then both series converge or diverge. So you're looking at the limit of the original series divided by bn, the one you picked. Let's simplify a little bit. That's limit n times 2n plus 1 over 1 times 3n squared plus n. 2n squared plus n over 3n squared plus n. That gives me 2 over 3, the limit, which is greater than 0. Again, look at the dominating terms. So both converge or diverge, since summation of the comparing series, which was 1 over n, diverges. So this is divergent by the p-series test. Then my original series in the problem divergent as well. So let's do two quick ones again to fix these notions, and then we're going to finish with the root test, but with just one example. The root test follows the same framework. The only difference is that you take the limit differently, and it's suitable for series that have n at an exponent. So powers, for example, something in terms of n raised to the power n. Those tend to be more appropriate for this test. They tend to work better that way. All right, so let's do two quick examples again related to this. And again, slow down and maybe rewind just to reinforce a little bit the whole notions we encountered so far. So suppose we look at this alternating series test. Because it's made of only polynomials, we know that the ratio test fails. I don't even try it. The limit will be 1. Again, if you're not convinced, apply it and see what happens. It's just made of polynomials, the ratio test will fail. Let's see if I can use the absolute convergence test. So let's look at the series that is made of absolute value of what I had there. So I end up with the summation of 1 over n squared plus 1. Okay, how do you deal with this one? Well, here you could use the comparison test. You could notice maybe immediately that this is going to be less than a series which is convergent. If you don't spot that, then use limit comparison test with the series made of dominating terms. So basically I'm looking at bn equals 1 over n squared, and I'm comparing the 1 over n squared plus 1 with 1 over n squared. I'm doing limit comparison test. Don't confuse this with the ratio test. Okay, again, the ratio test fails. All I'm doing now, I'm comparing the series with positive terms with the one that I picked myself that contains just 1 over n squared. And if I'm lucky to obtain the limit to be a positive number, and the limit will be 1, a positive number, then I know that both converge or diverge. So since summation of 1 over n squared converge, then summation of 1 over n squared plus 1 converge, again by the limit comparison test. And then that means the original series, the alternating series, is absolutely convergent, right? I don't have to use any different test just for the alternating series, because I proved directly using the limit comparison test that it is absolutely convergent. So compare this example with the one that I'm going to write here, summation from 1 to infinity minus 1 to the n 1 over square root of n, let's say plus 7. Ratio test fails again. It's made of square root of polynomials again. We can look to see if it's absolutely convergent. Take the absolute value of that, and that gives me a series with positive terms. What tools I have at the disposal? Well, I can use the comparison test. Let's say you cannot figure it out if because the inequality needs to be in the right direction. Typically, the rule of thumb is to just try limit comparison test just like before. So I'm going to compare with the series made of the dominating terms. So compare with summation from 1 to infinity 1 over root n, and then use, just like before, limit comparison test. So I'm going to take the limit as n goes to infinity 1 over root n plus 7 divided by 1 over root n, which is the same as times root n over 1. You look at the dominating terms, plus 7 here. The dominating terms are the same. The limit is 1. It's a positive number. They both converge and diverge. This is divergent because it's a p-series with p less than 1. Hence, the original is divergent as well. Okay, the original. What I mean is, let's not get ahead of ourselves. So what I'm talking about here is that the summation from 1 to infinity 1 over root n plus 7 is divergent. So basically the original is not absolutely convergent. Okay, so let's slow down for a moment. The original is not absolutely convergent. That's all we established so far. But is it just convergent or conditionally convergent? Well, the answer is yes. We could do this mentally. By alternative series test, it is convergent, therefore conditionally convergent. Why? Because 1 over root n plus 7 is decreasing and going to 0. We're going to have a review of all these tests, obviously, on the next lecture. But notice that that's why you need to have that handout, because these tests will basically come up together in the problem and, in various ways, essentially. So before I move on to the next page with the root test, again, let's review these two examples. We started in both cases with an alternating series. In both cases, the ratio test failed. Then we could look directly at the series with positive terms. And then for that, we use the limit comparison test. In the first case, we had convergence, and then game is over, right? Because if it's absolutely convergent, then the original is convergent. There is more work to be done on this last example because it was not absolutely convergent, right? So again, ratio test failed. We look at the one with positive terms. We use the limit comparison test. We concluded divergent. So all we establish is that it's not absolutely convergent. But then I still have to go back then to the original and see by other means if it's convergent or not. And it was, right, by the alternative series test. So let's stay tuned for the root test now. All right, so for the root test, like I said before, it's very similar. The only difference is that given, like I said before, a series with positive or negative terms, you're looking now at the limit of n as n goes to infinity of the nth root of absolute value of an. You can actually prove that the limit is the same as the one for the ratio. It's just that in some cases it's easier to compute this one here. So instead of taking an plus 1 over an, you can take the nth root over nth root of the absolute value of an. And you do this root test if you feel like this way to compute the limit is easier, this limit, because the conclusion is the same like before. So again, you have three cases. If the limit is less than 1, then the original series an is absolutely convergent. If the limit is greater than 1 or infinity, then the summation from 1 to infinity of an is divergent. And just like before, if the limit is equal to 1, the test is inconclusive, or the test fails. So the only really difference is the limit itself. Now, here are examples of series that are suitable for the root test. Basically, if you notice something in terms of an to the power n, something close to that, that tends to be more suitable for the root test, because the nth root will essentially eliminate this exponent. So for example, you could have summation from 1 to infinity, let's say minus 2n over n plus 1, or let's say over 3n plus 1 to the power 5n. You notice that you can write essentially everything as a power of n. So that might be suitable for the root test. Here's another example which I'm going to do now. Let's say you have summation from 1 to infinity, n squared plus 1 over 2n squared plus 1 to the power n. If you use the ratio test, that could be quite tedious to do that limit. But again, with the root test, especially in this example here, it's much more straightforward. So let's actually do this example. So by the root test, we're looking at the limit as n goes to infinity of the nth root. Again, these are positive terms, so I'm not going to bother with the absolute value. Nth root of the an itself. Now, nth root cancels with n, with the exponent inside the radical. So this ends up in the limit of just n squared plus 1 over 2n squared plus 1. Again, if we compare the dominating terms, this limit ends up being 1/2, which is less than 1. Therefore, it is absolutely convergent. Here's another one that may be more suitable for the root test. Let's say summation from 1 to infinity n 5 to the 2n over 10 to the n plus 1. And again, if I look at these exponents, it might be better to just use the root test or the well, actually, in this case, probably, let's see which one is easier. Because I have nth root, yeah, of n. Maybe this is better with the, yeah, this is better with the ratio test. So how about I leave this as an exercise with the ratio test? If you set out the limit of an plus 1 over an with the root test, ratio test, this should be 2.5, which is greater than 1, so that's divergent. So try this on your own. Sometimes things are obvious by other tests. So for example, yeah, let's finish up with another quick example. So let's say I have summation from 1 to infinity. of, let's say, n squared plus 1 over n, let's say 2n squared plus 1 over n to the power n. This is kind of like a funny example, but this obviously works with the root test, right? Because you could take the limit as of the nth root of 2n squared plus 1 over n to the power n. This crosses out, and then you have the limit of 2n squared plus 1 over n, which is actually infinity, right? If you look at the dominating terms. So that's divergent. So I want to end up with this example because you should never lose sight of the easy way out when you study the convergence of a series. That's why we're going to have a next lecture with a review of all those convergence tests. Because remember, we have also the divergence test, the first criteria that we learn in this chapter, which simply states that, you know, as long as an doesn't go to 0, then it's divergent. You don't have to do any computation of limits or anything like that. And I can tell from the beginning here that this basically goes to infinity because it's really infinity to the infinity, right? I mean, the inside goes to infinity, raised to the n, that's also infinity. So I could have said from the beginning that since the limit of the sequence that is summed up in the series is not doesn't go to 0, clearly the series is divergent. So more than one test can be used, then it's important to use the one that gives you less work to do. For the next lecture, make sure you prepare a handout with all the convergence tests so we can have a review of what we learned so far. So that's it for today.